about the lab from Friday on that Nernst equation. And the ramifications of that. And then we need to kind of like finish up some odds and end things on different formats, how questions are asked, and introduce you to a new re-dox table. Same idea, but it's just more on it. And then what we have left is gives free energy, which we'll cover tomorrow. And then we've got a big lab on the end of this week. And then we've got electrolytic cells, which are the opposite of voltaic cells because you have to dump energy into them. We got a lab on that, and it's like a comprehensive redox lab final, and then the test. So we still have a ways to go. So here's what I wanted you to see out of that computer simulation where you had Ag and silver ions, and then you had zinc and the zinc and the voltmeter. So first off, you have to start off with the right balanced equation, because if your balanced equation is wrong, everything is going to be wrong.
Oh my goodness.
So, and one of the things you've got to be able to do is use that redox table. So what you should end up is 2Ag plus zinc turning into Zn2 plus 2Ag. Okay? So when you get done with any redox reaction, I can't emphasize this enough. It has to balance on both. Okay? It has to balance on number of particles and charge. If it doesn't, it's wrong. Okay? It's like, it isn't like, we suggest that mass be conserved. It isn't a suggestion, it's a law. It isn't we suggest charge is conserved. Okay? No, it's a law as well. So when you get done and your charges don't add up, stop. Okay? It's not right, I promise you. Now, you can have situations where your charges add up and they're still wrong, but if your charges don't add up, you know you're wrong. Okay? So it's just a little step. So, knowing this, basically, and again, there's a couple of ways you can look at this in terms of how this is going to play out. So when you get to number 9, you're going to use that Nernst equation, E equals E naught 1.56 volts minus 0.0592 over 2 times the log of your zinc ion concentration divided by your silver ion concentration squared. Now, here's what you're going to do wrong, okay? You're just going to put the silver ion concentration down here, and you're going to forget about that 2, and you're going to forget the square of that silver ion concentration. And you all sit there and you go, Mr. Brookhamp, you won't do that, you lie. Okay? You lie. It's exactly what you're going to do, and I tell you not to do that, and you say you won't, but you're going to. But that's why you have to have the balanced equation. Now, in this situation, there's only 2 things that are solutions on both sides. You have a silver ion over here, you have a zinc ion over here. You can also run into situations like, let's say, for example, let's say that you had an additional hydronium ion. Let's just say, okay? Like, let's say, for example, you have hydronium ions over here when you get done. You don't, but let's say you did. So if you had hydronium ions over here, you would multiply by the hydronium ion concentration down there. Or if you had hydronium ions here, you'd put the concentration of those hydronium ions. So in this situation, there's just one, but don't look at this and go, oh, we can only ever have one product or one reactant that we worry about the concentrations on. No. We only worry about, we have 1 and 1 because that's all that we have, okay? You can have more than that, and given the circumstances. So here's what's going to happen on number 9. So you've got a silver ion concentration on number 9 of 0.001, and you have a zinc ion concentration of 2. Okay? So I don't care how you explain this. You pick the method that works best for you. So if you're into a social experiment explanation kind of thing, you can sit here and go, okay, well, the silver ions are pulling electrons because of the fact that this silver ion is gaining electrons, it's being reduced, okay? So that means this is your cathode, and here's your anode, and we all know that the electrons move from the anode to the cathode. So from a party perspective, you can say relative to the standard conditions, where it's 1 molar, there's not a lot of ions over here pulling electrons, but it's very crowded over here with the zinc. So it's just like, electrons don't have much desire to go because of the fact that it's really not all that cool of a party, and it's crowded. So electrons are like trying to talk themselves out of going, okay? Now, in contrast to that, if you want to go with a mathematical model, you can go, okay, well, I'm taking, then this whole thing is Q. When you take 2 and divide it by 0.01 squared, that gives you the value of Q. Oh, okay, cool. So the other way that you can explain it in terms of this is that Q is going to be a number bigger than 1. So I'm going to take 1.56 minus a positive value out of all of this. I'm going to subtract that from 1.56. E is going to be less than E naught. So if you want to go with a mathematical approach, that's cool, okay? I don't care. Just pick the one that makes the most sense for you. Then you're going to reverse it. Then you're going to have a whole bunch of silver ions, you know, blowing up your phone going, hey, wow, big party, come on, let's go, right? And then you look out in the hallway and it's not very crowded, and you go, oh, I like this. This speaks to me, okay? Got a lot of people having a good party, and it's going to be easy for me to go. You're going to go. If you want to go mathematically, you're taking the log of a value less than, Q is less than 1, Q is a small number. You're subtracting a negative value, E is bigger than E naught, okay? Pick one, I don't care. Then on that silver cell with that one, again, just realize Mother Nature wants to maintain equilibrium. So you've got 0.001 and you've got 2. There's your voltmeter, boom. Look at that, go, wow. Mother Nature's out of equilibrium. She is not happy at this point. And then you ask yourself, what can Mother Nature do to get back in equilibrium? Oh, you can raise the concentration of these ions and drop the concentration of those ions. Then figure out the mechanism. Oh, I've got to make more ions over here. So that means I've got to take silver and turn that into silver ions. Over here, I've got to decrease this, so I've got to take silver ions over here and change that into elemental silver. Now, when you get to question 6, where you add the hydrochloric acid, okay? When you look at how this is calculated, E equaling E naught, which is 0, minus 0.0592 over 1, because it's just Ag plus, times the log of Q, okay? If you're going to change E, the only value you can change is Q. That's it. It's the only thing you can change. You can't change the 0.0592. You can't change your N value as long as it's silver and silver. And E naught is just going to be 0. Oh, okay. So the only way I can change my E value is if I change my silver ion concentration. So when you take those silver ions and you add hydrochloric acid to it, realizing that hydrochloric acid is a strong acid, ask yourself, wow, is the hydronium going to react with the silver? Most likely not. They're positively charged. They're going to go like, go away. Nothing's going to happen there. But what you want to ask yourself is silver going to react with the chlorine and form a precipitate? That's when you have to just do a little bit of research and go, oh, let me see if silver chloride is soluble or insoluble. That's going to determine the answer. So silver chloride is soluble, nothing's probably going to happen. You diluted it a little bit, but probably not going to see a big change. If silver chloride is insoluble, the concentration of your silver ions is going to drop, or your silver ions is going to drop like a rock because you're going to form a precipitate. What does that do to your silver ions? What's going to happen to... Okay, any questions on the lab? Evan?
How would we explain which one is the anode without saying that's where oxidation occurs?
That's about all you can do.
Well, it specifically says that on number 10.
Oh, on number 10. Okay.
It's impossible.
So what I was looking for on number 10, okay, was that I wanted you to realize why oxidation is occurring. That's what I want you to get at, okay? Yes, that is where oxidation occurs, but why is oxidation occurring at that particular cell? It was the why, not the what. I thought you were asking about another question. Okay. All right, anything else? Once, twice sold? Okay.
Chemistry.
I've got a solution of silver nitrate, and I'm going to drop into that a piece of copper. Okay? So what I want to try and figure out is, will a reaction take place? Okay? So let's just start with that. So the first thing you got to be able to figure out is that what form is everything in. So I've got a solution of silver ions, and I have a piece of elemental copper. So how these questions are sometimes asked is that, like in this one, is Ag plus capable of oxidizing copper? Okay? So in other words, fundamentally what we're asking, when that silver ion comes up to those copper atoms, okay, and that's what it is, it's copper atom. Is this silver ion going to have enough of an ability to take electrons away from the copper, and then the rule is, though, the copper has this code that says, here's the story, you give up the electrons, you're kicked out of the club. Okay? What?
Evan's making it for me.
You'll find out. Evan's feeling goofy.
Don't worry about it.
Don't read the papers tonight.
Oh, I'm already in the bed.
You did something to my paper?
Bro,
That's on
imagine.
top. Go look in the basket.
After all, you said you like stapled your paper.
Yeah, we gotta get this on video, bro.
Is that
I
mine?
know it's yours.
I did not touch it.
I know it's yours. Handwriting.
Yeah.
He didn't staple it.
I've witnessed this.
Prank vid. Viral prank vid.
Do you know why?
Frank.
You know why?
Why
Thanks,
would-
Evan.
They do things like this, and they giggle.
You like to be on the street.
Wait, who's going today?
I'm harassed regularly in this classroom, Berg.
Sure, what?
I'm harassed regularly.
Do you know why?
What are you trying to say?
All I asked was, do you know why?
No, I do not.
I do.
We all know on
If
film.
you really want me to answer that, I will. Okay, anyway, so back to our story. So, I'll take this and I'll pass this around. And it's made this really, really nice, oddly enough, silver crystal. And here's the other thing that's happening. What do you notice about the tint of the solution?
Green.
It's turned bluish, right? Almost like a copper nitrate
Who
solution.
said green?
Well, bluish, okay, right?
Guess who said
There's
green,
definitely a hint of blue to it. So, if you want to answer this question, number one, you can just do the experiment. Okay, is Ag capable of oxidizing this? So we do the reaction, we see silver. It's like, okay, clearly something is taking place. So the rule is that this silver went in here and said, hey, give me your electrons. Copper says, fine, I don't like them anyway. So, but once the copper goes from elemental copper, gives up its electrons and turns into a copper ions, notice that that has a different color to it. So if it's elemental copper, it, oddly enough, looks like copper. But when that copper turns into an ion, it changes its interaction with light, and then it appears blue. So I'll pass this around just because it's kind of cool. Just don't shake it too much or this overall falls off. But it's just kind of cool to see. So the answer to this question then is yes. Now, if you have a reduction chart, you should be able to use that reduction chart. So what I gave you on that handout that I just handed out is a more complete redox table that actually lists the more complex ions, the polyatomic ions like the dichromates, the permanganates, the hydrogen peroxides, that type of thing. But it's still a reduction table. But it has the actual elements and the compounds on it. So it's actually more of a tool than just your basic glue. So on the test, you will have the standard one that you're used to, but you'll also have this one that has all of the compounds on it as well. So here's the story. If you look at Ag plus 1 electron, so what's the standard reduction potential for this reaction?
1.99.
1 point what?
99? Huh? Point 8?
I like 0.80 better.
That's Ag2 plus.
Oh. Oops. I just saw the first silver one, sorry.
Okay?
It's okay.
So that's a positive number. So does it want to go, Zach, you drink that, I will choke you.
Does it taste like the Gatorade though? Because there's a Gatorade color that comes in exactly that color.
It's my favorite flavor.
No.
But
So, does this reaction want to go in the direction that it's written? Yes. Okay? You got a feeling it's pretty good. So do you think Ag plus is a good reducing agent or a good oxidizing agent?
reducing. Oxidizing.
Oxidize.
Agent. It reduces.
No, wait.
Because it reduced.
Oxidizing agents like to be reduced.
Yes, oxidizing agents contain what
Wow, that
is
is very
reduced.
pretty.
Okay? So that's the flip. So silver ions are good oxidizing agents because of the fact that they're going to take electrons. Now, where's copper relative to Ag plus if you want to play the over-under game? Under. So Cu2 plus 2 electrons turning into elemental copper. What's the value for that?
0.34.
0.34
34?
volts. Now, which is still positive, okay? It's still positive. It wants to go in this direction, but it's not as positive as the silver is, okay? So because of this, the other thing that you want to look at is that this reaction couldn't take place. In what I had, why could that reaction not take place? When I took that piece of copper and dropped it into the silver ions, why could Cu2 plus not turn into elemental copper? Yeah, I dropped in elemental copper. I didn't have any copper ions to begin with. This reaction could not have taken place because of the fact that I don't have copper ions. I took a piece of copper and dropped it into silver ions. So the only way this could happen is if this does get reversed, okay? Then, now here's where you look at your E0 values. As soon as this gets reversed, what happens to the value of that E0 value? It changes into a Now when I add those together, you're going to get 0.46 volts, which is a positive value. If you get a positive E naught value, the reaction is going to take place. Okay? Got that one. Cool. Okay. Now I'm going to start with copper ions. Okay? Give that a quick splash. Burn a few copper ions. And now I'm going to drop a piece of magnesium ribbon. So now, I put a piece of magnesium ribbon into a solution of copper ions. Is anything going to happen? Yay or nay?
Yes. Yes. Yes.
Where's the magnesium?
Well, I can clearly see that the copper, the magnesium's turning like a reddish brown.
No.
So, if you look at what happens, so basically, here's the question. It's kind of the reverse of the first question. Is Cu2 plus
That's manganese. Oh no, it's right there. Okay.
capable
No wait, that's a.
of
I'm gonna say that's mercury.
oxidizing magnesium? But the odd thing about these questions is that they never put like the end of it. But is Cu2 plus capable of oxidizing magnesium into Mg2 plus ions? So the question always stops, is oxidizing magnesium? You just have to know, oh, what's that going to end up with? What's that going to look like if this happens? So you play the over-under game. Where's the copper ions in relation to the magnesium? Way above it, right? So Cu2 plus 2 electrons in this case is going to be, because it's going to stay like that, is 0.34 volts. That's going to stay that way because of the fact that I have copper ions. Oh, cool. Now, I dropped in there a chunk of elemental magnesium. What's the only thing the magnesium can do?
Turn into M.
Get oxidized.
Yeah, turn into Mg2 plus 2 electrons. Now, because you reverse the oxidation state, or you reverse the reaction from the magnesium and turn it into Mg2 plus 2 electrons, what do you do with that E naught value? Turn it into positive. So what's magnesium's? 2.37. So you add those together, boom, there's your E naught value. That reaction is going to take place. Okay? Now, but what if I put magnesium ions? What if I dropped a piece of copper into a solution of magnesium ions? Anything going to happen? No, because basically the magnesium doesn't have the capacity to take the copper and have it react. This is why it's so important that you look at the oxidation states of these. What form are they in? So is copper 2 plus capable of oxidizing magnesium? All day long. Are magnesium ions capable of oxidizing copper? No. Okay, because of the fact that it's not thermodynamically favored, which is a fancy way of saying you have a negative E naught value. Evan?
Would you get the reaction to happen if you like put a bunch of like heat on it or something?
If you put enough energy into it, then you could reverse it. But I'm just saying, as far as being a reaction under standard conditions, not going to happen. You dump enough energy into it, you hook it up to a battery, then it could happen. But not without an external source of energy. Okay, so last one. Got another piece of magnesium. Drop that into some hydrochloric acid. So I got H plus and magnesium. Skippy, is this reaction going to take place before I pour it in there?
With just H plus and magnesium?
Yep.
I don't think HMG is a thing, so no. You mean MgCl? Is that a thing?
Well, is there a reaction taking place?
That looks like it is.
I think it is.
I guess then yeah, MgCl probably is a thing.
MgCl?
Because HCl.
Okay. Do I care about the
Oh,
fluorine?
a stupid one now, Eli.
Do I care about the fluorine?
I don't know.
Not part of the story.
Oh, I think. Oh, yeah. So it's not one of those ones that we have to remember.
No.
Oh.
Okay. So, look at this. What's the reduction potential of hydrogen? It's the easiest one to remember.
0.
0. Okay, that's our benchmark. Hydrogen is our cut point. That's 0. So, if I take H plus into magnesium, then the proton, which is a fancy way of saying a hydronium ion, comes up to the magnesium and goes, hey, yo, I need your electrons. Magnesium says, take them. So I'm going to form magnesium ions and hydrogen gas. Now, what if I take hydrogen, hydrochloric acid, and drop in a copper, penny, piece of copper, whatever? What's going to happen?
Nothing.
Absolutely nothing is going to happen. Okay? So, if you look at the big three that's used in jewelry, and gold is on this is on here, okay, AU. So if you look at the big three, if you look at gold, and if you look at silver, and you look at copper, where are all of those elements relative to hydrogen? Above or below? Above. This is why we use elements that are above hydrogen in jewelry. Okay? Because the reason that we don't use magnesium is because, or anything below that, zinc, lithium, sodium, whatever, is because water, as you all know, has a certain, even neutral water, has a certain concentration of hydronium ions, which is 1 times 10 to the minus 7th. So if you make jewelry out of anything that's below hydrogen, okay, and you have some of that in water, then that jewelry is going to begin to react as soon as you get it wet, okay, let alone put it in any kind of acidic solution, lemon juice, something like that, orange, like, oh man, I got lemon juice on my ring and it just dissolves, and it's also very exothermic reaction, and your fingers burn and bad things happen. So this is why, even if you look at building materials, oh, copper, oh, hey, let's use copper as a building material. Sodium, not so much. It's like, oh, we should build your house up out of sodium. That's cool, okay? Until it rains or it gets foggy and then your house just dissolves. Okay. All right.
Wait, why is the Statue of Liberty green?
Because it's made out of copper, and over a period of time,
I know it oxidizes, but like
copper will oxidize.
But like with what?
Just very slowly.
With what though?
Copper oxide. It forms copper oxide.
I know, but like what's it reacting with? Oh, it's just the air?
Yeah, just
Oh,
oxygen.
yeah, that makes sense.
Okay, now, elemental sodium plus chlorine gas versus sodium chloride. Are these two reactions going to play out exactly the same? If I take a chunk of elemental sodium and expose it to chlorine gas, is that going to be the same thing as me giving you a piece of salt?
No,
Why?
because on the salt they have charges.
Okay,
There's also double chlorine when they're not salt.
correct? Now, here's the story. Sodium chloride itself is very, very stable, okay? We use it all the time, okay? We use it to flavor soups, to cook with it, okay? We use it all the time. Sodium and chlorine are soluble in water as ions. So if I put this in water, okay, all that's going to happen is that you're going to get sodium ions and chloride ions. And it's going to taste better, okay? That's it. All that's going to happen. Now here's the difference. If you have elemental sodium, okay, is elemental sodium want to get reduced or oxidized? Ask me, does elemental sodium want to get reduced or oxidized?
It would like to get reduced.
So sodium wants to gain an electron and turn into Na1 minus.
No, I thought we were talking about chlorine.
No.
It would like to get oxidized.
Okay. Your alkali metals in general, especially your alkali and rare earth metals, want to get oxidized. They want to lose those outer shell electrons. So sodium really wants to turn into sodium ions and give up an electron, okay? Because that's when it's going to be most stable. So this is why a sodium ion is cool, okay? You don't have to worry about exploding. I take elemental sodium and drop that in water, it's going to violently react, okay? But if I took salt in water, hey, it's cool. Chlorine gas by itself, chlorine gas, does it want to get oxidized or reduced? Aspen.
Reduced.
Chlorine gas wants to get reduced. So chlorine gas wants to turn into 2 chloride ions and 2 electrons. So this is why chlorine gas in World War I was used as in gas warfare, biological warfare, because chlorine gas actually has this green nasty haze to it, and you inhale it into your lungs. The chlorines are looking to give away those electrons. Guess what your lungs do? Your lungs take in the electrons and bad things happen. So this is what I want you to see is the difference. Sodium chloride is completely inert. We use it for flavoring soups. Elemental sodium, you drop that in water, very violent reaction takes place. Chlorine gas, completely poisonous, bad things are going to happen. So that's the difference. It was like, well, is sodium poisonous? Well, it depends, okay? Are you talking about a sodium ion or are you talking about elemental sodium, okay? Would you want to ingest sodium ions? Yeah, no worries. I like a little flavor on my food. Do I want to ingest elemental sodium, have it react with the water in my stomach? Not so much, okay? That's what you want to see is the difference. Now, think very carefully before you answer this. Is a sodium ion, does it want to be oxidized? Okay? Or the other way I could ask this is a sodium ion a good reducing agent?
Yes.
It would want to, a sodium ion would want to get oxidized.
Yes.
You want to stick with that?
Yes.
Okay. So Evan, and if the sodium ion gets oxidized, what's it going to change into?
Wait, sodium ion. I thought we were talking about sodium. So then it would be.
My bad. I should have made that plus a little bit bigger.
Wait, it's happy. What do you think?
So does the sodium ion want to get oxidized?
Not really. It's good.
No, because if it did, what would it turn into?
Na2+.
Plus an electron. In your esteemed chemistry careers, have you ever seen Na2+? No. Do you know why?
What zinc can I get from a distilled?
Go into that room next door. Go to the center island. There's going to be a. You can go through that door. In the center island, there's a white knob. In the center island, turn that on.
Catherine, I saw you at Walmart. I
Okay,
think.
Yes.
Did I?
Your racial profiling?
Wait, maybe not. I thought I saw your combat
You
boots,
saw
and
an
I was
Asian
like,
person
no.
at
They had the
Walmart.
same exact haircut in the combat boots, but then I was like, okay, sorry. That's just gonna. Sorry.
okay. All right, so, would a sodium ion make a good, would a sodium ion make a good reducing agent?
No.
No, it's horrible, horrible,
Hey,
okay? Absolutely horrible. Sodium isn't going to give away another electron and turn into Na2+. plus. It's a horrible reducing agent, okay? Now, is sodium a good oxidizing agent?
No.
Okay? So think this through. Is the sodium, elemental sodium, is that a good oxidizing agent?
No.
Why not?
Because
what?
it wants to be oxidized.
Oh,
Okay.
yeah.
Because if it was a good oxidizing agent, what would elemental sodium do?
We would do.
A1
It would gain an electron and turn into Na1 minus. Do you ever see Na1 minus? No. Do you know why? It's not stable. Okay? It's like it already has one outer shell electron that it wants to get rid of. It's not going to get another one because then it's just like, oh great, now I have twins that I really don't like anyway. So it's not going to happen. So here's my question. Here's your reduction table. Okay? So up here at the very top you have fluorine, down here at the very bottom you have lithium. So I want you to think very carefully about this. Where would you look, and I'm going to give you 4 options. Where would you look to find the best reducing agent? Okay, I want you to find the best reducing agent. Would you look top left, like fluorine? Would you look top right, like the fluoride ion? Would you look bottom left, as the reactant here, or would you look bottom right over here? You want the best reducing agent you can find. Where are you going to look?
bottom right,
Bottom right.
Why?
because it wants to go the other way. And lose
Because a
electrons.
good reducing agent will do what?
Oxidize.
Give up its electrons. So you want to find over here, because this is a lithium ion, gaining an electron, turning into lithium. This is this big negative value. So, and here's the difference. So lithium is a great reducing agent. Okay? Lithium is a great reducing agent. What about lithium ion? Is the lithium ion a good reducing agent?
No.
No. Okay, lithium ions would be a horrible reducing agent because it's not going to lose another electron and turn into Li2+. So lithium is a good reducing agent. Lithium oxide or lithium 1+, horrible reducing agent. So where would you look to find the best oxidizing agents? So we've eliminated the bottom right. So are your best oxidizing agents top left or top right?
Top left.
Why?
Because they are going to be very, very willing to gain electrons.
Yeah. So the best oxidizing agents are top left. Best reducing agents are bottom right. Guess what we keep separated in the chemical storeroom? Those elements, because we don't want them to come together. Okay? Now, I can store lithium ions with chlorine ions, otherwise known as lithium fluoride. Oh, I could put lithium chloride as ions together. Oh, I could go into the storeroom and get a bottle of lithium chloride. Okay? That's cool. Those can exist together in a bottle. I'm not going to take elemental lithium and put it right beside a container of elemental chlorine gas. Okay? That's the fundamental difference. Okay.
Eat it?
Hydrogen's cheaper.
Should I?
Isn't that basically like a spatial?
Too bad I don't have like chopsticks right now. No, take it.
I guess that would work, huh? You wouldn't have to worry about surfaces.
Maybe I should start.
It goes a little bit beyond our, constraint of, money.
Okay,
How much would you need?
now, using that reduction table that I just gave you, you have three potential ions. Nitrate ions, silver ions, dichromate ions. Those are the three that you have available. I want you to rank them in order of increasing strength as oxidizing agents. Okay? Increasing strength. So in other words, when you get done, the one that you list last is the best oxidizing agent. The one that you start with is the least, has the least strength as an oxidizing agent. So again, what are you trying to ask them to do? Are you trying to ask these to gain electrons or lose electrons? So basically, when you get done, you want to list the one that's most willing to take in electrons. So let's start with that one. So if with allowing for what we just talked about, are you going to look for those that are on the top left or top right?
Top left.
Top left. So which one is highest on the top left? On that chart that I just gave you. The CR207, because what's that value? What's that reduction potential?
1.33.
1.33. Now, what's the reduction potential for nitrate? What is it? 0.96. And for silver, it is 0.8. So if my dichromate is going to be most willing to take in electrons, which one's going to be the least willing to?
Silver.
So you go silver, nitrate, dichromate. Got it? Good? Okay, stop that camera.
Look, if
Okay, are we going, Marilla?
yes.
Okay,
Is also kind of.
I only want you to do the ones that are circled. Okay? Only do the ones that are circled. Now, when you get to 35, okay, that very first one, you're going to calculate the E naught values. You have to calculate the E naught values for those reactions on 35 and 36. Calculate the E naught values. Use the chart use the one that I just gave you. Okay? Then you're going to tell me which ones are spontaneous and which ones are not spontaneous. And the ones that are spontaneous, if the reactions aren't balanced, then you need to balance them. Okay? So there's some conditions. On 35 and 36, you have 4 reactions. You are going to calculate the E naught value for both of them. Or excuse me, for all 4 of them. For the ones that are spontaneous, you need to balance those. If they're not spontaneous, don't worry about it. Okay? When you get to 49, okay, 47, same thing, you're going to use this chart, okay? So, like on 49, answer the following questions. Is hydrogen capable of oxidizing copper into Cu2+? Okay? You're just going to look at your chart and go, okay, hey, if I basically dump copper into a hydronium ion solution, is something going to happen? When you get to 51, notice the ions that you have available to you. You have sodium ions, chloride ions, silver ions, elemental silver, zinc ions, zinc, and lead. So on 51, it says, which is the strongest oxidizing agent? Notice on this one it says, give reasons for your answers. Okay? So on 51, you're going to look through and go, okay, hey, what's my best oxidizing agent? Tell me why. Which one is your strongest reducing agent? Tell me why. Which species can be oxidized by sulfate in an acidic solution? Again, it might be one element, it might be two, it might be three or four. Same thing with question D. So the only thing that's due tomorrow are the ones that are circled. And even on 50, only do A, B, and D. Don't do C on 50. Okay, kids.